We will discuss now the last lesson for chapter 1, which is the elementary matrices. Let us recall first the three elementary row operations for matrices. First, interchange two rows. Second, multiply a row by a non-zero constant. And the last one, add a multiple of a row to another row. Note that applying any or a combination of these to a matrix will result to an equivalent matrix. Now we have the definition for the elementary matrix. An n by n matrix is called an elementary matrix when it can be obtained from the identity matrix I of order n by a single elementary row operation. Example, for each of these given matrices, let us identify if it is an elementary matrix or not. If it is, then we describe the corresponding elementary row operation. So first, we have here the given matrix. Observe that from a 3 by 3 identity matrix, this can be obtained by multiplying the second row by 3. Since only one elementary operation is applied, then therefore this is an elementary matrix. Next, since this is a 2 by 3 matrix, therefore not a square matrix, then this is not an elementary matrix. Take note, an elementary matrix must be a square matrix. Now, how about this one? Letter C. Is this an elementary matrix? So note that from the identity matrix of order 3, this can be obtained by multiplying 0 to the last row. However, note that row multiplication must be by a non-zero constant. We have number 2 in the elementary row operations. So therefore, this is not an elementary matrix. Next, letter D. This is an elementary matrix. And this can be obtained from a 3 by 3 matrix by interchanging rows 2 and 3. Now, how about this one? This is an elementary matrix. Why? Because this can be obtained from a 2 by 2 identity matrix by multiplying the first row of the identity matrix by 2 and add it to the second row. Okay, so again, this is an elementary matrix. How about the last one? So observe that from a 3 by 3 identity matrix, this is obtained by multiplying the second row by 2 and multiplying the third row by -1. So since it involves two elementary row operations, so therefore this is not an elementary matrix. Next, representing elementary row operations. Let E be the elementary matrix obtained by performing an elementary row operation on identity matrix of order M. If that same elementary row operation is performed on an M by N matrix A, then the resulting matrix is given by the product EA, or E times A. For example, we have here an elementary matrix E obtained by interchanging the first and the second row of the 3 by 3 identity matrix. Also, we have a matrix A, and if we get the product EA, we get this matrix, which can be obtained also by applying the same row operation to yield this elementary matrix A, which is by interchanging rows 1 and 2. Again, the idea is we can perform elementary row operations to a matrix by multiplying on the left by an elementary matrix with size such that the multiplication is defined. Next, we have row equivalence. Let A and B be an m by n matrices, or B m by n matrices. Matrix B is row equivalent to A when there exists a finite number of elementary matrices E sub 1, E sub 2 up to E sub k, such that B is the product of E sub k, E sub k minus 1, and so on up to E sub 2 times E sub 1 times A. Example. Find a sequence of elementary matrices that can be used to write the matrix A in row echelon form. So again, we want to find elementary matrices A sub k, A sub k is minus 1, and so on up to E sub 1 times A, so that we can rewrite A into the row echelon form. Or if we have this matrix here, that should be in row echelon form. So we have here the A. Now what we do is we want to reduce this in row echelon form. Rewrite this one in row echelon form, and then we are going to write the elementary row operation being used and then the corresponding elementary matrix. So that is, we have matrix, we have here the elementary row operation, and then let us get also the corresponding elementary matrix. Okay, so remember we want to apply elementary row operation one at a time. Okay, so first, since we want a leading one to have a row echelon form of A, so we can interchange rows 1 and 2 of this matrix. So we write here, we have 1, negative, that's negative 3, and then 0, 2. We have 0, 1, 3, 5. We have just interchanged rows 1 and 2. Then copy row 3. Okay, so again, the elementary row operation applied is interchanging row 1 and R2 of the given matrix. Okay, and then the elementary matrix corresponding to this elementary row operation, so that is from an identity matrix which is a 3 by 3, since we have here 3 by 4 matrix. So that's the order M. So this is 3 by 4. So we want this order. So we have from the identity 3 by 3 identity matrix, we will use this elementary row operation. We will apply this elementary row operation to this to get the elementary matrix. Okay, so we have interchange only rows 1 and 2. So we have 0, 1, 0, 1, 0, 0, 0, 0, 1. Let us name this one as E sub 1. Next, what we want is, we want this to be 0. So what we do is, we multiply row 1 by negative 2 and then add to row 3 to get new row 3. So we multiply row 1 by negative 2, add to row 3 to get new row 3. So that is one elementary row operation. So 1, negative 3, 0, 2, 0, 1, 3, 5, and then we will have here 0. Okay, so we multiply this by negative 2, so that's positive 6. Then we add, so that's 0. We multiply this by negative 2. We add, so that's 2 times negative 2, so that is negative 4. Okay, and then we get the corresponding elementary matrix. That is, again, we will apply this elementary row operation to the 3 by 3 identity matrix. Let us name that one as E sub 2. Okay, so we multiply row 1 by negative 2, and then we add to row 3 to get new R3. Okay, so multiply by negative 2, so it's negative 2. We have 0, so we have 0 and then 1. Okay, so that is E sub 2. Next, since we want a row echelon form, that is, we have to have a leading one here. So what we are going to do is we will multiply this by 1/2. So that's 1, and then this is negative 2. Again, we multiply by 1/2 to get new R3. Okay, again, we will apply the same row operation, elementary row operation to the 3 by 3 identity matrix. So we multiply by 1/2, so that is 0, 0, 1/2. Okay, so notice that we have now a row echelon form of this given matrix. So therefore, if we are going to let this as our B, then we get B equals, so let us name this as B, equals E sub 3, E sub 2, E sub 1 times A. So you can check that if we multiply these matrices, we have E sub 3 times E sub 2 times E sub 1 times A, then the result will be this matrix B. So you do the computation. Next, we have elementary matrices are invertible. If E is an elementary matrix, then E inverse exists and is an elementary matrix. Note that the inverse of an elementary matrix matrix E, is the elementary matrix E inverse that converts back to the identity matrix of order n. For example, let us find the inverses of the following elementary matrices. So first, we have the E sub 1. So observe that E sub 1 is obtained by interchanging row 1 and row 2 of the 3 by 3 identity matrix. Note that we can perform the same row operation to convert back to the identity matrix. Thus, our E sub 1 inverse is equal to, we have 0, 1, 0, 1, 0, 0, 0, 0, 1. Again, we just interchange rows 1 and 2 of the 3 by 3 identity matrix. Again, we use this elementary row operation because this is the operation that converts E1 back to the 3 by 3 identity matrix. Next, we have E sub 2. We have here the given matrix. So the question is, how do we get this matrix from the identity matrix of order 3? So we obtain E2 by multiplying row 1 by negative 2 and add the result to row 3 to get new row 3. So to convert this elementary matrix E2 to I, we need to multiply row 1 by 2 and add the result to row 3 to get new row 3. We multiply, sorry, that should be 2. To get new row 3. So we apply this to the identity matrix of order 3. So that is, we have 1, 0, 0, 0, 1, 0. Okay, so applying this to the I3, so we get the inverse of E sub 2, which is equal to, we multiply row 1 by 2 and then add to row 3 to get new row 3. So that is, we have 2, 0, and then 1. Okay, so we have now the inverse of E sub 2. Next is we have E sub 3. So given this matrix, so E3 can be obtained by multiplying 1/2 to row 3 of the identity matrix, the 3 by 3 identity matrix. So to convert this back to the identity matrix, we need to multiply row 3 by 2. And so we apply that to the identity matrix of order 3. So we get the inverse of E3 rather. We have 1, 0, multiply the row 3 by 2. So that means we have 0, 0, 2. Okay, so we have now the inverses of the given matrices, elementary matrices. Next, we have a property of invertible matrices. So a square matrix A is invertible if and only if it can be written as the product of elementary matrices. Let us consider this next example. So find a sequence of elementary matrices whose product is the non-singular matrix A. Let us start in finding the corresponding sequence of elementary matrices to rewrite this matrix A in reduced row echelon form. So we write the matrix here. We have the elementary row operations, and then let us have the corresponding elementary matrix here. Okay, so again, we want to write this in reduced row echelon form. So let us start with making leading one in row 1. So that is, we multiply row 1 by negative 1. We have 1, 2, 3, 8. So what we did is we multiply row 1 by negative 1 to get new row 1. So we have here, note that the identity matrix of order 2, we have 1, 0, 0, 1. So the corresponding elementary matrix, let us call this as E1, E sub 1. So we just apply this to the identity matrix. So therefore, we have negative 1, 0, 0, 1. Okay, next, we want this to be 0. So we multiply by negative 3. We multiply row 1 by negative 3 and then add to row 2. So negative 3, then to get new row 2. So we have 1, 2, 0. Multiply this by negative 3. So that's negative 6 plus 8. So we have here 2. Again, we will get the elementary matrix, corresponding elementary matrix. So we apply this not to this matrix, but instead to the identity matrix. So we multiply negative 3 and then we add to row 2. So we have negative 3, then we have 1. Okay, so we just simply multiply negative 3 to row 1 and then add to row 2 to get new row 2. Next, we want leading one here, or we want this one. So we multiply by 1/2. So 1/2 of row 2 to get new row 2. So that's 0 and then we have, so that should be 1. And then the corresponding elementary matrix. So that is, we apply this elementary row operation to the identity matrix. So 1/2 of row 2. So we have E sub 3 there. And then we want this to be 0. So what we do is we multiply this by negative 2 and then we add to row 1. So we have row 1, negative 2 of R2 to get new row 1. Okay, so this becomes now 1, 0, 0, 1. So the corresponding elementary matrix is multiply this by -2 and then add to row 1. So we have 1, -2, 0, 1. Now observe that what we got here is the 2 by 2 identity matrix. So we will just have, from the previous discussion, this means that we have E sub 4 times E sub 3 times E sub 2 times E sub 1 times the original given matrix, which is our A, is just equal to, this one is just the identity matrix of order 2. So we have equal to I. And then from this, we can obtain our A as, we can multiply here on the left by E sub 4 inverse, then we multiply also E sub 4 inverse here, so we can, this becomes I, and then we multiply by E sub 3 inverse here, so and so on. So we will get A equal to E sub 1 inverse, E sub 2 inverse, E sub 3 inverse, and then E sub 4 inverse. Okay, and then that is just times the identity matrix. So let us see if we will get A if we multiply the inverses. Okay, so by the way, if we want to get the inverse of these elementary matrices, so let us have here E sub 1. Again, what we want is the inverse, so we will just apply the elementary row operation to the elementary matrix that will make this convert back to the identity. So we have, so E sub 1. So from this, we will get the identity matrix, the 2 by 2 identity matrix, if we multiply row 1 by -1. So we will apply it in the identity matrix 2 by 2. So therefore, we will have -1, -1, 0, 0, 1. Again, what we apply is we multiply -1 to row 1. Next, E2 inverse. So to convert this back to the 2 by 2 identity matrix, we want to multiply this by 3 and then we add to row 2. Okay, so we will apply that operation again. 3R1 plus R2 to get new R2. So apply that to the identity matrix. So we have E sub 2 inverse is equal to 3, then we have 1. Multiply this by 3 and then add here. We'll do the same for the inverse of E sub 3. So to convert this back to the identity matrix, we multiply row 2 by 2, positive 2. So we apply that elementary row operation to the identity matrix. So we will get that one as the inverse of E sub 3. And then lastly, for the inverse of E sub 4, so we can make the 0 to convert this back to the identity by multiplying row 2 by positive 2 and then add to row 1. Okay, again, multiply row 2 by 2 and then add to row 1. So therefore, we have 1, 2, 0, 1 as the inverse of the elementary matrix E sub 4. So let us see, we have here, we multiply the inverses, E sub 1 to E sub 4. So we have -1, 0, 0, 1, 1, 0, 3, 1. Okay, so we multiply these two, we have that one, so we will get -1, then this to this, 0, and then that, so you will just get 3, and then 1. Also, we can multiply these two matrices here, so we have 1, 2, 0, 2. Okay, and then multiply we will get, first we have -1. We multiply this to this. Then add the results. We multiply this row to this column, so that's -2. And then we multiply this to that. We have 3. Then last, we have the 6 plus 2, so that would be 8. Okay? So we got A, the original given matrix here. So this is the sequence of elementary matrices whose product is A. Next, we have the following equivalent conditions. So if A is an n by n matrix, then the following statements are equivalent. This means that if one of these statements is true, then the rest of these statements must be also true. So first, A is invertible. Next is the equation AX equals B has a unique solution for every n by 1 column matrix B. Next, we have AX equals 0 matrix has only the trivial solution. And we have A is row equivalent to the n by n identity matrix. And lastly, A can be written as the product of elementary matrices. The proof of this theorem will be left as an exercise.